Hi all, I'm Akanksha and today me and Richard Corneau will be joining you and talking about end-to-end resource accounting leveraging distributed tracing. Small introduction about me. I am joining you guys from Atlanta. I am 37 weeks pregnant and I'm really glad that I'm able to do this. Richard will be joining us later in the presentation. Before we start about resource accounting, let's start thinking what is it used for? Well, biggest thing that it's used for is planning for capacity. Why is it important to plan for capacity? Well, for a system like Facebook, which has grown from serving 10 million users in 2007 to around 3 billion in 2021, which is roughly a 30 times of increase, it's a very important problem. In order to power this growth, you can see in the blue line how our power consumption has changed. It's changed from leasing one data center in 2007 to having 10 plus worldwide in 2021. However, the change in power usage is very different from the growth in active users. For the first half, you can see that there have been a lot of efficiency changes which are able to account for and allow us to support this increase in growth. But then we too are adding power. But still, the delta is just around 10%, 10 times as compared to 30 times in user growth. Now let's get into more detail about what are the factors which affect planning for capacity. First and foremost, you need to take into account what is your demand. However, demand being dynamic, it's very hard to predict. You need to understand how the number of users will be changing for various products, but also understand how they will be engaging with our tools. For example, during COVID, because of the restrictions, we saw a significant increase in engagement within the Facebook family of products, and that changed just within a span of few months. Secondly, efficiency of the system also needs to be taken into account. We need to understand how efficient our system is currently, but also to understand how efficient it can be and account for that while planning for capacity. Thirdly, adding capacity itself is hard and takes time. You need to plan for building a data center. Also, you need to take into account that where should the data center be built? For example, you need to build a data center where you have enough electricity, enough water supply, but also land resources which can be acquired at a reasonable cost. You can't build a data center in the middle of Manhattan, but it can't be in the center of the Sahara Desert as well. The final twist, which is the most interesting one, comes from the architecture of the system itself, distributed systems. They complicate this equation so much that planning for capacity becomes a very convoluted process. Let's take a deeper look. This is a snapshot of what a distributed system might look like. You have Instagram Live and Marketplace all interacting with the same set of services. Same shared services like Cache, MySQL, storage are being called from both Instagram as well as Marketplace. They are powering billions of requests per second without any clear idea about which product is calling them, how, and by how much within that request cycle. This complicated architecture makes planning for capacity hard. Let's see what are the questions you would want to answer while planning for capacity. First and foremost, you want to understand what's the overall cost of a given product to Facebook's infrastructure. Once you know that, you would want to know which services get their demand from this product so that you can see how much resources these products are consuming in these various services. Only then you can answer questions like, if Instagram Live is expected to grow by X%, what is the overall capacity I need to add in the system to power that growth? You also need to know which services you want to allocate this growth to. Thus, we need the ability to look at the big picture while still retaining the capability to slice and dice this data by different views. Another view which is important is from a shared services perspective. You need to know that if these various products are growing by X, Y, and Z%, how these various shared services need to grow in order to support that scale. Thus, you need to look at the data from different perspectives so as to be able to answer planning for capacity not just at the products level but individual services level. Now, let's see how you could try and get to these numbers. One way to do this could be looking at single hop data to try and understand how a given product like Instagram is calling these services directly. We did this analysis and we realized that direct calls only provide you a very small percentage of view of that overall demand. Looking at overall transitive demand and direct demand, the difference can be as much as 16 times. Okay, well, even if you were able to get this understanding of what's the overall transitive demand of a given product into this service, how would you then do planning for capacity? Well, one way to do this is to do this manually. You collect these numbers for each of these services, then collect them, aggregate them for a service group, collect them for overall all the services within Facebook, and you can then account them in Excel sheets, and voila, you can do planning for capacity. Well, Facebook tried that. It does not work. Primarily, we have seen cases where a new product was launched, downstream services ending up not having enough allocated capacity for them, which then resulted in sites going down. So we know we need a better system. Now, let's see how that might look like. Richard will get into more details about that system called transitive resource accounting.
Thank you, Akanksha. My name is Richard Cornu, and I'm joining you out of New York City, and I've been working at Facebook for almost 3 years now. I'm going to talk a bit about transitive resource accounting, or TRA. So what is TRA? TRA is a system that builds on top of the distributed tracing platform Canopy. The goal of TRA is to collect end-to-end resource accounting metrics and attribute them back to the originating caller. So how does this work? Canopy provides a number of SDKs in the major languages supported here at Facebook. TRA uses these SDKs to instrument major front-end services like Instagram. When a request hits these services, it interacts with sampling logic, where we decide whether or not to start a trace. If we decide to start a trace, we create a tracing context, which simply is an ID that we add to the request header. And as this request propagates through our infrastructure, we check for the existence of the ID. If found, we generate a data event and then emit this to the backend. The backend then stitches together all of these individual events and creates a single trace, which allows us to view the request tree as a singular object. So TRA builds on top of this by working with profilers to collect resources counting or resource consumption metrics at each hop in the request tree. These data events are then all sent back to the tracing backend where they're in the same trace structure, but TRA builds custom processing pipelines to then aggregate and output these metrics into our own tables. So we know how to start a trace and understand the resource consumption along the duration of that trace, but we need traces for each product in order to do capacity planning for shared services like cache. So we've worked with Canopy to use their SDKs to start traces from all major front ends like Facebook, Instagram, and Messenger. On top of starting traces everywhere, we need to ensure that we're capturing traces all the time. This is because products have different peaks, and when doing capacity planning, we need to account for peak demand. So we set up sampling logic that looks at every request all the time and decides whether or not to start the trace. So on top of starting traces everywhere and starting them all the time, we need to ensure that traces continue to every service in our infra. This is a challenge because not all services can support tracing. And here we have an example where service B does not allow the trace to continue into our shared services like MySQL and storage. This can lead to challenges, especially in the MySQL case, where we do have trace data starting from service A, but we're missing coverage from service B, where we have partial coverage and doing our analysis. So now that we understand how tracing works, let's look at what the data provides us. So here we have a table that visualizes the two perspectives that we can take with this data. The top row is products like Facebook, Instagram, and Messenger, and on the side we have shared services like storage, MySQL, and cache. In the product view, we like to take a vertical slice. So here I am Instagram, and I am trying to understand what my total cost is across the infrastructure. We can use this data to do quota management and efficiency analysis of a product as a whole. Here we have a visualization of that data where we have a singular product that calls into a number of backend services. And now with distributed tracing, we understand which services are making up a majority of the cost and how to account for it. From the flip side, we have the shared service view. Here we're taking a horizontal slice in the table where I am cache and I want to understand what percentage of my demand is coming from the different front-end products. With this data, we can answer demand management questions as well as capacity planning, where I need to figure out how much I need to scale based off a front-end product's growth. Understanding my demand ratio for that product allows me to scale appropriately. Here we have a visualization of the shared service view where a number of products are calling into a single service, and we can break up that demand, not even just by product, but also the originating endpoint that is called in that product. So now that we see the data that we collect, Akanksha is going to dive into a number of the use cases utilizing this data to make insightful decisions.
Now that we have solved the high-level problem, we start off with, let's see what other use cases TRA can be used to. One thing that we have seen TRA is helpful in is planning for capacity for new feature launches. We mentioned in the earlier slides that this is something that initially we ran into issues with. The way TRA can help with this problem is by allowing users to collect TRA data in an A/B test scenario where for few users you have launched this feature while you have not for the rest. Doing this comparison, you can try and understand how capacity will be needed in the downstream services when you launch this new feature. For example, if you look at this new graph that we have, where different services, CPU utilization is shown, you can see in the pink lines that when you launch the feature, service A and B will end up needing more CPU by 5 and 8% respectively when the feature is launched week 5. You can do this by TRA. Another interesting thing where TRA has been found useful is to plan for capacity shortage events. What does that mean? Well, as we mentioned earlier, during COVID, we saw high changes in our demand of the products. This can lead to capacity shortage issues. In order to solve for that capacity crunch, we can selectively turn off few features in order to free up resources. However, how do you know freeing up which resources is important, or turning off which features will result in saving capacity in which services and by how much? Well, one way to do that is to turn off these features fleet-wide. But that would negatively impact user experience. That's where TRA comes in. You can turn off these features selectively for few percentage of the users, use that data to then predict how much capacity can be saved fleet-wide by turning off these features. Here is an example of the chart that we have for service X, where the pink line shows the resource consumption, CPU in this case, for in production traffic. Turning off few features, as shown in knob 3, saves you about 5 to 10% of capacity. However, if you go down all the way to knob 1, which ends up turning off a few more features than you want, will end up freeing about 25% of resources in this given service. You can get this analysis without having to degrade the performance for users everywhere within Facebook. Now, I'll hand it over to Richard, who will get into more details like key learnings and our future work.
Thanks, Akanksha. I'm now going to dive into some of the key learnings that we've made along the way in setting up this system. First is that tracing is not free, and it definitely adds an overhead to our requests. Second is that not all services support tracing, and this can lead to challenges in our data analysis. And thirdly is that not all services are bound by the same metric. So let's dive into these. First, tracing overhead. When a request hits a service to start a trace, we have to sample, set up coin flipping, do the coin flipping, and then as the trace continues, we have to send out these data events. This adds a computational cost to our infrastructure. So to account for this, we've done three things. First is we fine-tuned our sampling. So not all requests are traced, and we've set this coin flip value specifically to generate high enough value data downstream so that we can make our decisions. Secondly, we've worked with data scientists to create tracing overhead elimination models. So looking at historic data and and then looking at service-specific data, we estimate the overhead and eliminate it so that we have a representation of true cost. And thirdly, we've worked with Canopy to make tracing configurable. So not all data needs to be collected on every trace, and now this is configurable via a tracing policy where I can select what I want on my trace. Secondly, tracing is not supported everywhere. And these gaps can lead to issues when we're trying to understand absolute demand in a service. If we only cover half of the demand in, we are lacking in understanding when we're trying to do demand management or capacity planning for that service. And thirdly, efficiency metrics are not, or like different services are bound by different metrics. So TRA primarily focuses on compute or CPU instructions and cycles, and some services are bound by storage and memory. And these are areas that we're working on improving. Let's talk a little bit more about TRA coverage. So TRA right now covers about 60% of all of the power usage here at Facebook. We are trying to close this gap by adding sampling points to our non-user request-driven workflows. These include ML, cache updates, or nightly ETF pipelines that run. So we're working to add traces here to cover every bit of demand in our infrastructure. What are we working on in the future? First and foremost is closing this coverage gap and getting coverage everywhere. So we've started traces on our major front ends like Facebook, Instagram, and Messenger, and we're working with Canopy to utilize their new Erlang SDK so that we can cover WhatsApp. Secondly, we're trying to automate a lot of our workflows. So Akanksha detailed our A/B testing system for feature releases, and this requires some manual assistance today, and we want to make it a self-service model in the future, where a product engineer can just set up an experiment and understand and predict their cost of their future rollout. Thank you, and I hope you enjoyed.